Welcome back to this Biosystems Analysis and Modeling series. In this module, we are going to do a brief tour of probability distributions for describing random variables and talk about how we use this to represent variability in our models. Upon completing this module, you will be able to first understand what a probability distribution is and how to use them to characterize a random variable. Second, you'll understand the principles of fitting a probability distribution to a set of data. And finally, you'll be familiar with the basic idea of using probability distributions in stochastic modeling in Monte Carlo simulations. So, let's get started. Why do we need to consider variability in our models? Let's consider, for example, designing a culvert to accommodate expected flows. Note the use of the term expected, which is inherently a statistical term. For this example, let's examine the flow rates observed in the Oxnard Plain, a rapidly growing community in California. Looking at this data, we observe several things. First, there appears to be a general upward trend in the data, quite likely reflecting the increase in impervious surfaces resulting from the development that tends to increase the flashiness of the system, increasing maximum observed flows. But in addition to this trend, if we are just to design a culvert that can accommodate a 20-year flood in year 2020, for example, just extrapolating the trend line is not sufficient to this task. We also need to understand the range of flow rates we are likely to encounter and be able to characterize a flood that has a 1 in 20 chance of occurring in the future. We've seen before how to characterize trends in data. That is the regression analysis that we've discussed earlier in this course. Regression captures some of the variability of the system related to time, but clearly doesn't capture all of the variability in the data. To do this, we will need to examine the statistical properties of the data, for example, the peak flow and the maximum departure from the expected flow, and characterize mathematically the nature of the variability associated with this data. As it turns out, there are lots of situations in which we may want to incorporate variability into our models. Why is this important? Very simply, because many of the processes we may want to model may have elements that are best represented not by a single value, but by a distribution of values. For example, precipitation inputs into a cropping system can be highly variable, and if we want our models to reflect this variability, we need to have techniques for capturing and incorporating this variability into our models. Other examples include temperature or flow rate variability in bioreactors, or wildfire disturbances in an ecosystem. Take a second to identify processes that you are familiar with that might be highly variable. As you will see, variability exists all around us. We are often interested in characterizing the variability of an output of our models. This becomes clear when the questions we ask our models incorporate the language of statistics. For example, what is the likelihood of a cropping system failing in response to weather? Or what is the probability that the Willamette River will flood this year? What is the risk of experiencing a catastrophic wildfire in response to a seasonal weather trends? What design will allow us to accommodate a 20-year extreme event? We need techniques for both representing this variability and in propagating variability in inputs through a model to determine variability of associated outputs. We will start with a discussion on how to represent variability and finish with a discussion of how to propagate this variability through our models. To represent the variability associated with a random variable, we turn to probability distributions. Probability distributions are a way of representing the frequency of occurrence of values of a random variable. These are typically represented as a histogram, which plot values of a random variable on the horizontal axis and the frequency of which we would observe those values of the random variable on the vertical axis. Thus, a histogram gives us a sense of the likelihood of observing different values of a random variable. In the example shown here, for a random variable x, we see that we have a relatively low likelihood of seeing either very small or very large values of x, and a relatively high likelihood of observing values of x that are towards the middle of the range. Further, one can imagine a function that would characterize this relationship. This would be a function that for a given value of x would allow us to determine the likelihood of observing that value of x in a set of observations. We will name this function a probability density function, often referred to as the PDF. It is the function we described on the previous slide, characterizing the shape of the histogram, describing the frequency of occurrence of different values of x. A useful characteristic of the PDF is that we can use it to estimate the likelihood of observing a value in a given range. We do this by integrating the function between the two values in question. Graphically, we can represent this as shown in the figure here. Thinking in terms of likelihoods instead of frequencies, the area under this curve represents the likelihood of seeing any possible value of x. This likelihood is 1.0 or 100%, since all possible values of x are shown under the curve. It is also the integrated value of the PDF for x between minus infinity and plus infinity. The area under the curve between two values x1 and x2 shown on the plot is the likelihood of observing values just in that range alone. For this histogram, again we see that we are more likely to observe intermediate values of x, where most of the area under the curve is, and are less likely to see values at the lower or higher end of the range of x, where there isn't much area under the histogram curve. The integral of the PDF over the range minus infinity to a given value of x is called the cumulative distribution function because it accumulates likelihoods of values less than or equal to x being observed. It represents the area under the histogram curve, the PDF, to the left of any given value x. This turns out to be a useful function. We can characterize the probability of observing values less than or equal to x by solving this function for the given values of x. We can also calculate the probability of observing a value of x in a given range by simply evaluating the CEDF at the endpoints of the range and taking the difference between those two values. Note that the CDF always starts at 0 at minus infinity and always increases to a maximum value of 1. This is because there is always zero chance of seeing an observation of minus infinity, and as well looks at increasing values of x, the probability of seeing a value less than or equal to x always increases. The CDF always maxes out at 1.0 because at some point we've seen all possible values of x, so the probability of observing values less than or equal to that value is 100%. All values will be less than the maximum value of x. For example, suppose we wanted to determine the probability of the Willamette River reaching a maximum water level stage elevation greater than 30 feet at Corvallis in a given year. This is generally the stage at which the Willamette is considered as flooding. Assuming we had a PDF describing the frequency of observing different maximum water elevations over multiple years, or a CDF, they are two sides of the same coin since one is just the integral of the others. So if we have one, we have the other. But if we have these, we could solve the CDF for an x value of 30. That would give us the likelihood of observing a flow less than or equal to 30. Subtracting this value from 1 would give us the likelihood of observing values greater than 30 in any given year. For probability distributions, we are basically interested in shapes. In particular, the shape of the histogram of the variable that we want to treat as a random variable. Let's look at a couple of examples. We'll start with peak flows in a river, shown on the left. In general, we would expect the shape of the histogram to have certain characteristics reflecting the physical processes being represented. Flow values below 0 should not be allowed. Generally, we would expect observed flow rate values to be in a moderate range, but would occasionally expect very low flow years, but always greater than 0. Further, we would expect the occasional high flow year, but not as frequently as more moderate flow years. Finally, we might occasionally experience very large flow years, but this would be very infrequent. We could imagine that the curve shown on the left of the slide here would capture these characteristics of the observed system in this case. In contrast, consider the frequency of different levels of delay associated with an airline departure. Quite often, we would expect the airline to leave on time. Zero or minimal delays would have a relatively high frequency and therefore high probability of occurring. Occasionally, however, we would expect to encounter a moderate delay, and on rare occasions, we might experience a considerable delay. Plotting these frequencies as a function of the delay period would result in a PDF that looks something like the curve shown on the chart on the right-hand side of the slide shown here. There are many commonly used distributions. However, we can represent most probability distributions with just a handful of these. We will look at these next. The first, and probably simplest distribution, is the uniform distribution. This distribution is straightforward. Within the range of a uniformly distributed variable x, we are equally likely to see any given value of x. This means that the PDF is flat, since for any given value of x, the frequency of observing that value will be the same as the frequency of observing any other value of x in the range. A common use of a uniform distribution is to generate random numbers from other distributions, but this distribution is also useful as a first guess if you have no other information about the frequency distribution of the variable. Another common distribution is the exponential distribution. It has the advantage of being simple, requiring only a single parameter to parameterize. It is bounded on the left at 0. It is often used in hydrologic studies to characterize extreme values of such variables as monthly and annual maximum values of daily rainfall and river discharge volumes. The normal or Gaussian distribution is a familiar one to many people. It is the so-called bell curve that is used to describe phenomena that are distributed equally on either side of a mean value. The most common use of the normal distribution is to characterize the distribution of error in a regression analysis, but it has many other uses as well. For example, in hydrology, the distribution of long-duration river discharge or rainfall, monthly or yearly totals, often follows a normal distribution. The log normal distribution describes a random variable whose logarithm is normally distributed. Thus, it can have a similar general shape as a normal distribution, but it is generally skewed as a result of the log transform. It is often useful to characterize processes whose overall behavior is a result of many independent processes operating simultaneously. Like the exponential distribution, the log normal distribution is often used to describe extreme values of such variables as monthly and annual maximum values of daily rainfall and river discharge volumes. However, this distribution has many other uses where the overall behavior of a system is the result of many smaller independent processes acting together. For example, in economics, income of a population is generally distributed log normally. Population sizes of cities also tends to follow a log normal distribution. Repair times for complex systems also tend to follow a distribution of this form. We've looked at several commonly used continuous probability distributions, meaning distributions for random variables that are continuous rather than consisting of discrete values only. There are many more continuous distributions available that we won't review, but are described in many available stats books and statistical sites online. Additionally, there are distributions for describing discrete variables as well. For example, the binomial distribution is used to describe the number of successes in a set of observations where the outcome is binary, meaning a yes or no answer. We won't describe these discrete statistical distributions in detail here, but if you are trying to characterize a discrete as opposed to a continuous variable, you will want to familiarize yourself with some of these distributions. To use these distributions, we must first parameterize them. This means fitting a particular distribution to a particular dataset to find best fit values for the distribution parameters. This is done through a nonlinear regression process. The number of parameters to estimate depends on the distribution being fitted. For example, the exponential distribution has just a single parameter, lambda, but for the normal distribution, there are two parameters, the mean and the standard deviation. Procedures for fitting these parameters also depends on the distribution. For many distributions, parameters can be calculated directly from the data. Others require a more iterative approach. The details of these procedures are readily available on the web at sites like Wikipedia or in textbooks such as Law and Kelton. Further, most statistical programming packages have functions for fitting specific parameters. For example, distributions in the scipy.stats Python package have a fit function that will fit the given distribution to a set of data. Here's some simple examples of fitting a particular distribution. In the case of the uniform distribution, we need to fit two parameters, the minimum and the maximum of the data, parameters A and B, shown here. The maximum likelihood estimator, meaning the best fit value, is found simply by extracting the minimum and the maximum value from the dataset being fitted. These are, in fact, the best estimates of A and B. For the exponential distribution, only a single parameter is required, lambda. We can estimate the value of lambda for a given dataset by computing the mean of the data and then calculating lambda as 1 over this mean value. Once we have a distribution defined and parameterized, what can we do with it? One thing we can do is use the distribution to answer specific questions about the random variable the distribution describes. For example, suppose we have parameterized a log-normal distribution for describing the frequency of observing annual precipitation amounts over a multi-year observational dataset. With the fitted distribution, we can answer questions like, what is the probability of less than 1.5 meters of rain in a given year? Referring to the PDF shown in the upper right, this is really asking, what portion of the area under the PDF is to the left of 1.5? Referring to the CDF shown in the lower right, we can answer this by finding the cumulative probability values for a given rainfall level, which in this case yields an answer of 0.5, meaning there is a 50% chance that in any given year we will observe less than 1.5 meters of rainfall. We can also answer questions like, how much rain can be expected in 4 out of 5 years? In this case, we would look at the CDF and find the probability value we are looking for, 0.8 in this case, since we wanted a 4 out of 5 probability, and then determine the rainfall level that is necessary to achieve this probability, 1.93 in this case. Another common use of probability distributions is in stochastic modeling. The basic idea is to describe one or more model inputs as a probability distribution and then running the model repeatedly, sampling a random value from the distribution each time for input into the model. We collect the outputs from the collection of model runs and develop and analyze the probability distribution associated with these outputs, with the goal of understanding how the variability associated with our input variables manifests itself, perhaps in concert with other sources of variability, or through interactions with other components of the system captured in the model. This process is generally referred to as a Monte Carlo simulation. For example, suppose we want to understand the yield variation we might expect when growing a crop in a rain-fed only cropping system with no irrigation. And we have a model that estimates yields based on precipitation inputs. Assuming we have a historical record of precipitation patterns for our site, we could use this data to select and develop a probability distribution describing the frequency we would expect to see for different levels of rainfall. Once we had parameterized this distribution, we would be ready to start our Monte Carlo simulations, generating a stream of random precipitation values sampled from our distribution and using those to run the model multiple times, collecting yield results as we go. At the end of the process, we generate a probability distribution describing our outputs to answer questions along the lines of what we saw on the previous slide. Here's a slightly more explicit description of the workflow associated with a Monte Carlo simulation analysis. The first step is to gather an observational data set describing the variable or variables that we want to consider as random variables in our model. The next step is to select an appropriate distribution and fit the data to those distributions. At this point, we are ready to start a simulation. We generate a random value, or values if we have multiple random variables, from the distributions and use these as inputs into our model. We run the model with this input or inputs, collecting the resulting model output or outputs of interest. After we have made a sufficient number of runs to adequately characterize the output variability, we stop the simulation loop and turn to characterizing the statistical properties of the output or outputs of interest. Generally, in Monte Carlo simulations, we run hundreds or possibly thousands of different simulation runs to ensure that we've adequately sampled the space of our input variables. To conduct the Monte Carlo analysis, we need an ability to generate streams of random numbers to conform to a given probability distribution. The general procedure for this is to generate a uniformly distributed number between 0 and 1 and plug that number into the inverse of the cumulative distribution function. Each new uniformly distributed number between 0 and 1 is used to generate a new random value conforming to the desired distribution for the variable. Doing this multiple times will produce a stream of random variables we can use as inputs into our model. In practice, most programming languages have statistical libraries that will generate random numbers for a given distribution. For example, distributions contained in Python's scipy.stats package all have a RVS function that takes as an input the number of random variates desired and returns an array of random values conforming to the given probability distribution. To recap, in this module, we examined probability distributions and their use in stochastic modeling. Key takeaways include the following. First, many systems have variability for which it may be important to capture in an analysis. When we are concerned with ranges of values, likelihood of achieving different outcomes, or frequency in which an event is likely to occur, we generally need to include considerations of variability in our analysis. Second, we use probability distributions to describe variability associated with a random variable. Probability distributions describe the likelihood of observing different values of the variable. They come in two related forms: the probability density function, or PDF, that describes the frequency of which a particular value of a variable is likely to be observed, and a cumulative distribution function, or CDF, that is the integral of the PDF and that describes the cumulative likelihood of observing different values of that variable. Third, different probability distributions are appropriate for different variables. Selecting an appropriate functional form and fitting that form to data is a necessary step in characterizing variability associated with any given variable. Fourth, we can examine statistical properties of a variable by analyzing its probability distribution directly. Once we've selected and parameterized the distribution, we can use it to determine things like likelihood of extreme events, design flows, and similar characteristics of the random variable. Finally, we can use probability distributions to drive models and to characterize the variability of model outputs. This process is called Monte Carlo simulation and is commonly used to understand how variability propagates through a system.